pause the video and try the warm-up. Going with pre-cal, what you probably do is factor and reduce and get rid of that 0 divided by 0. Now plugging in the 2 to the leftovers, we get 4. So here's a case, we had 0 divided by 0, and that is not 0, and it was not undefined. What you just found was the limit, it's not the actual value, but the limit at a removable discontinuity on a graph. Today we are starting chapter 8, which is a lot of L'Hopital's rule, and there is a lot of process involved in L'Hopital's. L'Hopital's rule was actually developed by his teacher, Johann Bernoulli. L'Hopital was taking private lessons from him, and he published the book, so his name is attached to it. We're going to use L'Hopital's rule to deal with things like 0 divided by 0, infinity divided by infinity, and things like this. Is infinity stronger than 0, or is 0 stronger than infinity? Sometimes when you multiply them together, you might get 1. And infinity minus infinity, infinities are not the same size. You can get infinity, you can get 0, you can get a half, you can get all kinds of things. And 1 to the infinity, oddly, 1 times 1 times 1 for sufficiently large values of 1 can equal things like 2. Again, we will see. Okay, this was from the warm-up. If we try to plug in and substitute, we get 0 divided by 0, but pre-cal, we can do this. Now, L'Hopital's rule is another way we could have solved that. This limit, then L'Hopital's rule says if we get 0 on the top and 0 on the bottom, we can do the derivatives of both and try again. So here's using limit definition of derivative backwards. If this derivative and that derivative, there's limit definition at derivative at a point A, I can pull the limit off of both of them and then multiply by x minus a over x minus a. So it flattens out. But from the beginning, we said f of x and g of x evaluated at a or 0, the original thing. So going backwards, it's just a quick proof for L'Hopital's, and you don't need to know how to do that, you just need to know how to use L'Hopital's. So if the functions, two functions evaluated at a particular point are both 0, we can apply this thing of L'Hopital's, which is doing the derivative of the top and the derivative of the bottom and evaluating that point again. There are other conditions that also can work. If the function on the top is positive infinity and the one on the bottom goes to negative infinity, you can do the derivatives that way also. This is not a new way of quotient rule, making sure you realize that. We can't normally just do the derivative of the top over the derivative of the bottom. That is not quotient rule. This is evaluating a limit, a very special case. And if we were doing this is not at all how we have added fractions. However, is there a context where this makes sense? Yes. If your team won 4 of the 5 last games and one of the next 2 games, your overall record would be 5 out of 7. Is this how we add fractions? No. Is this how we do derivatives of a quotient? No. We are evaluating a limit at a point where special conditions apply. Either the function, 2 functions at a go to 0, or the 2 functions at a go to some flavor of infinity, then we can do this L'Hopital's rule. So, as I said at the beginning, L'Hopital's has a lot of process. On the AP exam, they have gotten more and more particular, just like rounding, they really want to see all of this spelled out. So taking the numerator apart all by itself with its own limit, this evaluates to 0. And the bottom, even though it's trivial, yes, you need to pull this apart and do this. So I have 0 on the top and 0 on the bottom. L'Hopital's applies. That means I can do the derivative of the top over the derivative of the bottom. All right, so up top, multiply by the power, lower the power, and multiply by the derivative of the stuff inside, which is a 1. The derivative of the 2 goes away. Derivative in the denominator is a 1. Now plugging in 0 for the top and bottom, everywhere that x is, which is only here. 1 over 2 times the square root of 4, 1/4. So in this case, 0 divided by 0 was 1/4. In the first example, it was 2. Okay, pause the video, write it down, try and apply L'Hopital's rule, do the formatting of pulling the numerator out for both. Showing the limit, 0 over 0, L'Hopital's does apply. And right here it says 0 from the left. Sometimes it matters, sometimes it doesn't. In this case, it doesn't. Derivative of sine is cosine. Derivative of 2x is 2. Now I can plug that 0 in. Cosine of 0 is 1, and the 2 is there, so here we get a half. Gets trickier. So write the problem down, and again, pull apart the numerator and denominator to see if L'Hopital's applies. Top and the bottom both go to 0, so L'Hopital's applies, so I can do the derivative of the top, which is complicated. Multiply by the power, lower the power, multiply by the derivative of the stuff inside, which is just 1. This 1 goes away, and the derivative of negative x over 2 is negative 1/2, and the denominator is 2x. And as I didn't say anything but underlined it, repeated use. You need to pull the numerator and denominator out again. Plugging in 0, I get 1/2 times the square root of 1 minus 1/2, which is 0. And down here I get 0. So again, L'Hopital's applies. Derivative of the denominator is easy. Numerator, that half goes away. Here, multiply by the power, which is negative 1/2. Lower the power from 1/2 to 3/2. Plugging in 0 for x, I get negative 1/2 times positive 1/2 divided by 2, which is negative 1/4 divided by 2, which is negative 1/8. The big thing about L'Hopital's, you need to know when to stop. This is the reason AP makes a big deal that you check each time that, well, the numerator, 1 minus cosine x evaluated at 0. Well, yes, 1 minus 1 is 0. And taking the denominator, checking at 0, x plus x squared. 0 plus 0 squared is 0, so L'Hopital's applies. Do the derivative of the top and bottom, and then checking again. Sine of 0 is 0, but the denominator is 1, so this in the end evaluates to 0. If you keep going, you will get it wrong. So please know when to stop. This is the reason they make you check. Okay, this one, they might be mean and ask you to know what these graphs look like from the left. Cosecant is sine upside down. So cosecant's going to go like this, bubbles pop. So the limit as x approaches pi from the left, cosecant x appears to go to positive infinity. This right here. Cotangent, graphically, it goes to negative infinity. And this, even though the sign on the infinities mismatch, L'Hopital's applies. So the derivative of the top, derivative of cosecant, just like secant sucks, it takes itself into its own derivative and brings a friend. Cosecant's worse. It's negative. It puts itself in its own derivative and it brings a friend. Derivative of cotangent. Derivative of 1 is 0. Derivative of cotangent is negative cosecant squared. Negative over negative cancels. Cosecant over cosecant cancels. And here I would do some pre-cal. Cotangent is cosine over sine. Sine down here, cosecant that is, becomes sine at the top. And cosine of pi is negative 1. Here is another kind of indeterminate form. L'Hopital's works when we have one function divided by another and we get a 0 divided by 0, or infinity divided by some flavor of infinity. So right here I need to put it into a form that L'Hopital's is going to apply. So I need to do common denominator. I get x minus 1 minus natural log of x over natural log of x times x minus 1. Taking the numerator and testing. And as x approaches 1 from the right of x minus 1 minus natural log of x. 1 minus 1 minus natural log of 1. You need to know that natural log of 1 is 0. So 1 minus 1 is 0, minus another 0 is 0. Denominator, checking 1 from the right. Sorry, I think I said left earlier. This becomes natural log of 1 times 1 minus 1. That is also 0, so L'Hopital's applies. Derivative of the top is 1 minus 1 over x. Derivative of the bottom. And plugging in 1, okay, I get another 0 divided by 0. So we need to pull them apart as we approach 1 from the right. 1 minus 1 over x is 0. As we approach 1 from the right in the denominator. 1 minus 1 over 1 plus natural log of 1. Well, that's 0 minus 0. So again, L'Hopital's applies here as well. So as x approaches 1 from the right, derivative of the numerator, the 1 goes away. This, multiplied by the power, which is negative 1, so that becomes positive, lower the power. And down here, simplified a little. Distributing, get 1 minus 1 over x plus natural log of x. So the derivative of this, derivative of 1 is 0. Derivative of that, negative 1 x squared, did it just above, plus a 1 over x. Now plugging in 1, in the numerator I get 1, in the denominator I get 1 plus 1. So when we do infinity divided minus infinity, so this was infinity minus infinity, I ended up with a half. There are aspects of limits that we don't ever explicitly teach you, even though we've done some of it in pre-cal, we don't really point it out. I can move this limit into a function if I didn't cross over a place where that variable was. I still haven't crossed a variable, so I am going to move this inside the square root as well. So I can move limits inside and outside of functions as long as I'm not crossing over where an x is, right? So now there's x's, can't do anything, but look at this. From pre-cal, what is the horizontal asymptote? Is it top heavy, bottom heavy, or equal? This looks bottom heavy. So this is sine of the square root of this whole thing comes out to be 0. Square root of 0 is 0. Sine of 0 is 0. So we can do this thing with limits. Okay, if we look at this and we plug in infinity, 1 divided by infinity is basically 0. So this is kind of like 1 plus 0 to the infinity, which you would think 1 to the infinity equals 1. However, it doesn't. So I'm going to do e, a natural log of this, because I can. And I said a moment ago we could move the limit around. Previously, I moved it into the function. Here, I'm moving it out. Why? Because this is a moving target to a moving target. It's hard to manage. I want to bring that exponent down. And now I can do stuff with this. Right here, I do not have a fraction. I don't have something where L'Hopital's is going to apply. So there is a trick, and you will need to use this. I'm going to multiply by 1 over x on the top and bottom. When I distribute that up here, I get natural log of 1 plus 1 over x. In the bottom, I get 1 over x. And doing the tedious L'Hopital check, the limit as x goes to infinity in the numerator. As we go to infinity, this 1 over x goes to 0. This natural log becomes natural log of 1, which is basically 0. In the denominator, 1 over x, as I get closer and closer to infinity, I have 1 cookie to share among infinite people. That also becomes 0. Now L'Hopital's applies. It does not apply when we're in this form, but here when I have a fraction over a fraction, and those become one of a few special conditions, one of them being 0 over 0, L'Hopital's applies. So I will do L'Hopital's again here. Derivative of the top, 1 over the stuff inside, times the derivative of the stuff inside. Derivative of 1 over x is negative 1 over x squared. That's all in my numerator. And the denominator, again, the derivative of 1 over x multiplied by the power lower the power. These guys cancel. And this becomes e to the limit as x approaches infinity of 1 plus 1 over x. Well, I can finally plug infinity in. 1 over infinity, basically 0, so this becomes e to the first, which is known as e. So all the way back up here, 1 to the infinity, in this case, for sufficiently large values of 1, it became 2.7 and change. It became e. Okay, so enough of exploding your head for today. The homework assignment is a 2-day assignment, but I suggest you start some of the textbook problems, which is day 94, Page 431, 1 to 27 odd. I suggest you do the first 5 or 6.